This call is now being recorded.
Okay, sir, you
Good
can
morning.
proceed now.
Good morning, all dear students. Good morning, Honorable Dr. G.K.Awari, sir.
Good morning.
Yes, student. Today we have with us Honorable Dr. G.K.Awari, sir. Sir is Head of Department of Automobile Engineering Department at Government Polytechnic, Nagpur. And today, sir, is going to discuss further topic of fluid mechanics. That topics are helpful to your GATE examination. So now I request Honorable Dr. G.K.Awari, sir. So kindly proceed with further presentation.
Okay. Thank you, Ritesh, and thank you, Vishwajit. This is the second lecture in the series of fluid power and fluid machinery. The last time we have covered the topic of the fluid properties, okay, and the control volume, conservation of mass, mechanical efficiency, okay, and the stability of the floating and submerged bodies. All these topics we have covered in the last Sunday in the 2 hour span of time. Now the remaining topics in this fluid power is basically the Bernoulli's theorem, okay, application of the Bernoulli's theorem, then dimensional analysis, Buckingham method, Rayleigh method, and then the flow through pipes. So this topic in today's 2 hours of discussion that I will be taking up, and at the end we will have the discussion on the various sample gate examinations as well as the examples from the gate. So I hope all of you are ready. Let me present my screen. विश्वजीत, आवाज येतो ना माझा? Hello.
Yes, sir.
Am I audible?
Yes, sir. येऊन राहिला.
Thank you.
Yes, sir, you are audible. Screen is also
आवाज
visible,
येतोय
sir.
सर clear.
Thank you. My screen is visible. Presentation is visible.
Yes,
Yes,
sir.
sir.
Okay. So once again, congratulations to the honorable management, honorable principal, and the head of mechanical engineering department, Professor Ritesh Bankurkar, Vishwajit Ambade, vice principal Pragati Patil, for taking the initiative to organize these such kind of lectures under the GATE scheme or the under the Prerna scheme for the students and for the benefit of all the students. Okay, so I hope that all of you have hello, all of you have applied for the GATE examination. It is happening in the month of Feb 2021. You know that, and the I think it is open also, so that you can apply for the GATE examination. And let us prepare for the GATE examination very seriously, so that you can have the good score in the GATE examination, and you can go for the higher education, like pursuing the MTech from the IITs or the NITs. So today's my topic of discussion is basically the dimensional analysis and the Bernoulli's theorem. So the contents of my today's presentation, I will be covering energy of a fluid in motion, Bernoulli's theorem, application of Bernoulli's equation to the venturimeter, orifice meter, pitot tube, dimensional analysis, Rayleigh method, Buckingham method, GATE question. And in the next slide, I will go through the basically the flow through pipe. So energy of a liquid in motion. So the energy in general may be defined as the capacity to do work. Okay, though the energy exists in many form, at the following are the from the subject point of view, that is three parts of the energy. One is nothing but the potential energy, another is nothing but the kinetic energy, and third one is nothing but the pressure energy. So from the fluid power point of view, we have categorized into the three parts, that is potential, kinetic, and the pressure energy. And you know that the energy can either be created nor be destroyed, but one form of energy can be converted into the another form of energy. So therefore, we can see in subsequent slides, subsequent presentation, that the pressure energy getting converted into the kinetic energy. We have studied these examples also in the subject of fluid power. So what do you mean by the potential energy? Potential energy of a liquid particle in motion. It is the energy possessed by a liquid particle by virtue of its position. If a liquid particle is z meters above the horizontal datum, okay, the potential energy of the particle will be z meter kilogram, okay, briefly written as mkg per kg of the liquid. The potential head of the liquid at that point will be the z meters of liquid. For example, if you take your application of hostel or your household or in your house or the flat scheme, what happens, that overhead tank is there. In the overhead tank, the certain quantity of water is there. Okay, in that case, the level of water in the tank, and from the bottom level, it is basically the datum, that is nothing but the potential energy. So when you are not using the water at the outlet end, at the user's end, so the energy possessed by a liquid is nothing but the potential energy due to the datum difference. Similarly, okay, the water in the lake, okay, even though it is a stationary, but it possesses the potential energy, water in the lake. So energy, potential energy is due to the difference in the z, that is datum, and it is expressed in terms of the meters of liquid. Then kinetic energy of a liquid particle in motion. If the energy possessed by a liquid particle by virtue of its motion or velocity, okay, if a liquid particle is flowing through a mean velocity of v meter per second, then the kinetic energy of the particle will be v square by 2g. Okay, and velocity head at that point of velocity will be v square by 2g meter of that liquid. So we have considered the examples of the nozzles also, wherein, okay, when you allow the water to flow through the nozzle, there is a formation of the jet. Okay, so at inlet, the velocity of the energy, velocity energy or kinetic energy of the liquid is less, but at the outlet, the kinetic energy is more, because this pressure energy is getting converted into the kinetic energy. So kinetic energy is nothing but due to the velocity energy, and it is expressed in terms of the v square by 2g meters of that liquid. Then the pressure energy of a liquid particle in motion. It is the energy possessed by a liquid particle by virtue of its existing pressure. If a liquid particle is under a pressure of P kilonewton per meter square, that is kilopascal, then the pressure energy of that particle will be P by rho g, mkg per kg of the liquid, where W is the specific weight of the liquid. Pressure head of the liquid under that pressure will be P by rho g meters of the liquid. So this is the pressure energy. Then what is the total energy of a liquid particle in motion? The total energy of a liquid in motion is basically the sum of its potential energy, kinetic energy, and the pressure energy. So mathematically it can be expressed as E is equal to Z plus V square by 2G plus P by W. So you can see that Z is nothing but the potential energy, V square by 2G is the kinetic energy, okay, and P by W is nothing but the pressure energy. So summation of these three energy, it basically gives us the total energy of a liquid particle in motion. Then similarly, total head. So total head of a liquid particle in motion. The total head of a liquid particle in motion is the sum of, again, potential head, kinetic head, and pressure head. So it is expressed in capital H is equal to Z datum head plus V square by 2G plus P by W. Now Let us come to the Bernoulli's equation or the Bernoulli's theorem. Take an example of this pipe. This pipe, okay, it is different in diameter. You can see that it is larger in diameter at the exit end, at the inlet end. It is smaller in diameter, and this is the Z1 datum level from the center of this particular inlet. This is the Z2. So datum difference is also there. Z1 is less, Z2 is more, A2 is more. Okay, area, cross-sectional area at point 2 is more, and A1 is less. Now V1 is there at cross-sectional point 1 and V2 at cross-sectional point 2. So what the Bernoulli's equation says, that this equation was developed by Daniel Bernoulli in 1738. It states, for a perfect incompressible liquid flowing in a continuous stream, the total energy of a particle remains the same while the particle moves from one point to the another. So this statement is based on the assumption that there are no losses due to friction in the pipe. So mathematically, this Bernoulli's equation can be expressed as Z is equal to V square by 2G plus P by W is equal to constant. So you know that the Z is potential energy, V square by 2G is kinetic energy, and P by W is a pressure energy. Under this assumption, what assumptions are made by the Bernoulli's? Assumption number 1 is no work or heat interaction between the fluid element and the surrounding takes place. The fluid must be incompressible, okay, like liquids or the water. Okay, it is an incompressible fluid. Friction by viscous forces has to be negligible. So what the Bernoulli's equation suggests that, okay, that is the P by rho G plus V square by 2G plus Z1 is equal to C1 constant, which means that in the earlier point which we have seen at the two cross section, if you write P1 by W plus V1 square by 2G plus Z1 is equal to P2 by W plus V2 square by 2G plus Z2. Because total energy of a fluid, it remains constant. This is what it has been stated by the Bernoulli's theorem. Now, the same thing is being given here. That is P1 by rho G plus V1 square by 2G plus Z1 is equal to P2 by rho G plus V2 square by 2G plus Z2 is equal to HF. What is HF? HF is nothing but the head loss due to friction. Flow through the pipe presentation, we are going to see this HF also. So this HF is added in the now right hand side of the equation, means P2 by rho G plus V2 square by 2G plus Z2 plus HF. We cross section 2 पे add किया, because I have assumed the direction of flow of water, flow of liquid in the upward direction from left to right. If I assume the direction of flow of water from right to left means top to bottom, in that case this HF will be getting added into the left hand side of the equation. So basically HF will represent the frictional work done, okay, work done against the fluid friction per unit weight of a fluid element while moving from a station 1 to 2 along a streamline in the direction of flow. So the Bernoulli's theorem says that the total energy of the fluid, it remains constant at various cross section. Now let us see the applications of the Bernoulli's law or the Bernoulli's equation. This is the first application of the Bernoulli's theorem. That is orifice meter is there. These are all the flow measuring devices. Orifice meter, Venturi meter. Okay, these are all flow measuring devices. So you can see that this is orifice plate wherein small hole is there inside this plate. Okay, and there is a abrupt change in the cross sectional area. क्योंकि ये अगर पाइप में लगा देंगे and when there is a flow of liquid through this pipe, what will happen? This orifice plate will offer a obstruction to the flow and there is a sudden reduction in the cross sectional area. Okay, because of that the pressure difference is created, which is measured with the help of this U-tube, and we will be able to calculate the flow rate of the liquid through this pipeline. Similarly, this is the second application of the Bernoulli's law, that is the Venturi meter is there. So you can see that converging section, throat section, diverging section is there in the Bernoulli's equation, Bernoulli's theorem, and the manometer is being connected to the two parts of the Venturi meter so that we can measure the pressure difference, and accordingly we can calculate the flow rate of the water, flow rate of the liquid. Now let us go to the Venturi meter. let us see the venturimeter. The diagram is in front of you. So basically, venturimeter is a device used for the measurement of flow in a pipeline based on principle of Bernoulli's theorem. It consists of three parts: converging cone, short cylindrical throat, and a diverging cone. So this basically, this is nothing but your inlet section. Okay, are you getting it? The diameter of the inlet section is equivalent to the diameter of the pipeline where it is connected. This is your outlet section. Again, the diameter will be same as that of the outlet diameter of the pipeline. But here you can see that this portion is different. This is called as the converging section. This is the throat section, and this is the diverging section. So when the fluid it passes through this converging section, there is a reduction in the cross-sectional area. Because of that, the pressure energy gets converted into the kinetic energy. So this converging section, it is like a nozzle. You might have observed the fire brigade. I will quote the example of the fire brigade. In fire brigade में hose pipe के end में एक nozzle लगी रहती है. तो nozzle से jet formation होता है. तो वो कैसे होता है? Okay, fire brigade में pump भी है. Pressurized fluid, when it is allowed to pass through the hose pipe and when it passes through the nozzle, there is a formation of the jet, and the kinetic energy or kinetic head of the liquid or the water, it is being increased. So one form of energy can get converted into the another form of energy. So that in fire brigade हमें fire extinguish करना है, application वहाँ पे है fire extinguish का, तो इसलिए हमें वहाँ पे it should reach to the maximum distance. So therefore we convert the pressure energy into the kinetic energy. As in case of the Pelton turbine also, we use the nozzle for converting the pressure energy into the kinetic energy. So you can see that this is the throat section, and this is basically the diverging section. At this moment, you can observe that the length of the diverging section is more than the length of the converging section. So let us see now the converging section and the diverging section. The function of the converging section is to accelerate the flow and create a pressure difference between the inlet to converging cone and the throat. And the angle of diverging cone is 14 to 20 degree. So normal angle which is kept in the design of the venturimeter, it is 14 to 20 degree. So here in this part of the in this portion of the venturimeter, the fluid is getting accelerated. Okay, this is the throat section, that is short cylindrical throat. The function of the throat is to stabilize the flow and facilitate the provision of pressure tapping. Okay, means here the pressure tapping is being attached so that the pressure difference from the inlet to the throat section, it can be measured, and the diameter ratio, that is throat diameter, it is 0.4 to 0.7 times of diameter of the pipeline. Okay, this is the normal what I can say, the thumb rule or the normal design. That is capital D is the diameter of the pipeline, small d is the diameter of the throat. So diameter of the throat is 0.4 to 0.7 times of the diameter of the pipeline. Therefore, now we will go to the diverging section. The function of diverging cone is to reduce the velocity and increase the pressure to its original value to the extent it is possibly practical. So angle of diverging cone is from 5 to 7 degree. वहाँ 14 से 20 डिग्री था, यहाँ 5 से 7 डिग्री है. So there is a difference between the angle. Here the angle is less, means the length of the diverging cone is more than the converging cone. So why such a difference is there? The reason being is that in this part of the venturimeter, the fluid is being retarded. Means what happens, the kinetic energy, the velocity energy of the fluid passing through the diverging cone, it is reduced, and then we are regaining our pressure energy. So therefore, during the retardation of the fluid, there is a energy losses are there, eddies formation are there in this part of the venturimeter. To minimize the energy losses, to minimize the eddies formation, what we do is that the angle of the diverging cone is kept as 5 to 7 degree compared with the 14 to 20 degree in case of the converging cone. So this is basically the reason. Then the, for example, where I am taking now the venturimeter, this is the inclined venturimeter, what the picture you can see, inclined venturimeter, inclined pipeline is there. and in the inclined pipeline, the venturimeter is being connected. So this is the cross section 1, inlet portion. This is throat portion, cross section 2. Here in this case now, the datum difference is also there. This Z1 is there, which is lesser or lower, smaller value compared with the Z2. And this is the delta H, difference in the manometric liquid, two limbs of the manometer. So let the velocity and pressure at the inlet section, section 1 are V1, P1 respectively, and those at the throat section are V2 and P2. Now applying the Bernoulli's equation between these section 1 and section 2, that is P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2. Bernoulli's equation says that total energy remains constant. Yeah, equal की sign दे दी. Then taking the velocity term and pressure term on one side. So V2 square minus V1 square divided by 2g is equal to P1 minus P2 divided by rho g plus Z1 minus Z2. So where density of the fluid flowing through the venturimeter from the continuity equation, okay, what the continuity equation says, rho 1 A1 V1 is equal to rho 2 A2 V2. But naturally the liquid is incompressible. So rho 1 is equal to rho 2. So rho 1 is equal to rho 2 means rho factor will get cancelled. So what is the value of the Q? Q is nothing but A2 V2 is equal to A1 V1. So by putting this value in this equation, finally we will get the velocity of the water, velocity of the liquid at the throat point is equal to, okay, 1 by square root of 1 minus A2 square divided by A1 square multiplied by square root of 2g in bracket H1 minus H2. What is H1 minus H2? It is the basically manometric differences. A2, A1, you know that it is the area at the throat section and area at the inlet section. So H1 is equal to P1 by rho g plus Z1 and H2 is equal to P2 by rho g plus Z2. And finally, the volume flow rate of the through the pipe is given by Q is equal to A2 V2 is equal to A2 divided by 1 minus A2 square divided by A1 square in bracket square root of 2g, okay, H1 minus H2. This is the equation of discharge of flow through venturimeter. Actual discharge can be calculated by multiplying the theoretical discharge with coefficient of discharge. The value of coefficient of discharge in case of venturimeter, it varies from 0.91 to 0.99, depends upon the condition of the flow and losses. So what is the coefficient of discharge? Actual discharge divided by the theoretical discharge is nothing but the CD, coefficient of discharge. So theoretical discharge will be more than that of the actual discharge. So what are the merits and demerits of a venturimeter? The recovery of pressure is near original value, okay, because CD is very high. Loss of energy is minimum, okay. Demerits are its cost is high, occupies more space than orifice meter, okay. Uses and application: calculating flow rate of a fluid in a tube, setting the flow of gasoline in ignition system or for motor vehicle. If the field of medicine has also designed, venturimeter is used to measure the rate of flow of blood flow in the arteries. So in the medical field, in the various field, even in the industry, to measure the flow of fluid, okay, flow of liquids, in case of the or flow of water, we can use this venturimeter. So this is the first application of venturimeter. Let us come to the second application of venturimeter. That is nothing but the orifice meter. So orifice meter, it may be installed in a pipeline with a minimum of trouble and expenses. So what you can see is that this is the orifice meter, and this is the orifice plate. Okay, it is like a simple plate is there, where the small hole is there, and there is a sudden contraction in the area. For example, the flow of liquid is there from this direction. Flow of then what will happen? This orifice plate, it offers obstruction because of the small hole. There is a decrease in the area, and then due to this, the pressure energy gets converted into the kinetic energy, and at this point, the point of the vena contracta, the velocity will be more, okay, pressure energy will be minimum, and with this 2 manometer we are measuring the pressure difference between the pressure difference between this point 1, that is inlet section, and the point of vena contracta. And you can see that in case of the orifice meter, these are all circles, these lines which you can see, these are all eddies formation, means energy loss is being taking place. Why it is taking place? In case of the venturometer, there is a gradually conversion of the pressure energy into the velocity energy. But in case of orifice meter, there is a sudden reduction in the area of the pipeline because of this orifice meter. So therefore, this energy loss is more in case of the orifice meter. Okay, and that's why the orifice meter is having the less value of the CD. So what is the value of the CD? Coefficient of discharge 0.6 times of 0.6 to 0.65, means actual discharge is 0.6 times of the theoretical discharge. So orifice meter is a device to determine the rate of flow through the pipe. It consists of a flat circular plate which has a sharp-edged circular hole called orifice. It is fixed concentric to pipe. The orifice diameter is generally kept half of the diameter of the pipe, and it is based on the same principle as explained in venturometer. But compared with the venturometer, this orifice meter is economical, less space is required, okay, for fitting. एक लेक्चर घेतो मी 12:30 संपत्ती माझं लेक्चर. So difference between an orifice meter and the venturometer. For venturometer, there is no contraction area of the jet is always equal to the area of the throat. So while the orifice, it is much more affected by the variations in CC, and it is by the variations in CV. Okay, so after the two applications, let us go to the next application, that is a pitot tube. So in the pitot tube, you can see that it is a simple tube, simple device used for measuring the velocity of a flow at the required point in a pipe or stream. It is also called as the impact tube or stagnation tube. So there is always a MCQ based on this pitot tube in the GATE examination or the IS examination or the competitive examination. So try to study this topic well. What you can see is that, okay, like a nozzle-like shape is given over here at the entrance of the pitot tube. Because of that, what will happen? The flowing fluid, it will come to at rest at the inlet point of the pitot tube. So that point is nothing but the stagnation point. And due to the stagnation point, the pressure difference will be there, which is recorded in the pitot tube, and further we calculate the velocity of the fluid flowing through the pipeline. So the basic pitot tube consists of a tube pointing directly into the fluid flow. As this tube contains fluid, a pressure can be measured. The moving fluid is brought to rest as there is no outlet to allow flow to continue. This pressure is the stagnation pressure of the fluid, also known as total pressure, okay, or the pitot pressure. The measured stagnation pressure cannot itself be used to determine the fluid flow of velocity. Okay, however, the Bernoulli's equation states that stagnation pressure is equal to static pressure plus dynamic pressure. So this is about the first part of my today's presentation. I have covered the topic of Bernoulli's theorem, Bernoulli's law, its principle. Okay, then I have covered the application, that is venturometer, orifice meter, as well as the pitot tube. So let me take the review like last time, and let me ask you some question, and then we will proceed with the next part of my presentation. Okay. So can anybody answer that which topics we have covered till now? In the first part of the presentation, which topic we have covered? Vinay is there. Vinay, Sanket Dhokle. Hello, who is speaking?
Energy of liquid in motion, Bernoulli's equation.
हाँ, Tamgadge, हाँ, Bernoulli's equation we have studied. Yes, very good. Again, Yes,
Orifice
applications
meter,
of Bernoulli's
Venturi
theorem,
meter.
orifice meter, Venturi meter. Very good, Tamgade. Okay. So, and the pitot tube. Now, the next question is that what is the purpose of the pitot tube? What for pitot tube is used? Any other?
Measuring the pressure of flow.
Measuring the no,
Pressure of
no,
liquid flow.
it is wrong. No, I told you this is the competitive examination. Pitot tube is not useful for measuring the pressure or the flow rate of the liquid.
Measuring velocity of the flow of the required velocity of
Yes,
point.
Amir. Okay, very good. Okay, pitot tube is used for measuring the velocity of the fluid flowing through the pipe. Okay, am I right? And Venturi meter and orifice meter are used for measuring the volume flow rate or the flow rate of the liquid flowing through the pipe. Okay, is that clear? The next question to you is that Venturi meter का CD कितना होता है? Normal value, which I have quoted in my presentation. What is the normal value of the CD value of the Venturi meter?
0.60 to 0.65.
No, orifice meter. Okay, it is Nirvant Moon. It is right for the orifice meter, 0.6 to 0.65. But in case of the Venturi meter, yes, Siddhant is online. Siddhant, 0.9. Huh?
Sir, 0.9. Sir, 0.91 to 0.95.
0.9 to 91 to 95 like that. Okay, normal range. Pawan has also told. Very good, very good. So next question to is that think logically before you give the answer. Okay, if you are staying in the flat scheme and your building is having a tank where it contains 100 liters of water, there is no Venturi meter placed in the pipeline. Okay, now what you have done is that at the user end नीचे के फ्लैट में आपने या कहीं पे आपने वेंचुर मीटर पाइपलाइन में लगा दिया. वो वेंचुर मीटर जो पाइपलाइन में लगाया है उसका जो सीडी है, the CD is 0.95. Okay, the tank contains 100 liters of water. The CD of a venture meter is 0.95. So how much quantity of water you will collect at the user end? If you open the tap, how much quantity of water you will collect? Can anybody think over it? Think and then reply. Overhead tank contains 100 liters of water. In the pipeline, we have fitted a venturimeter having a CD of 0.95. CD is nothing but actual discharge divided by theoretical discharge. Okay, how much quantity of water you will collect at the user end? This is my question. Yes, can anybody answer? Anyone? There are 60 students in the class. Anyone from the girls side? Are there any girls today? Those who have joined today? Yes, Achal is there. Achal is online. So Achal, can you tell me what is the quantity of water which will be collected? Anyone? Abhijit?
Sir, 1.95 liters.
How much?
1.95 liters.
1.95 liters. 100 liters पानी है तो 1.95 liters कैसे मिलेगा बेटा? शुभम?
Sir, actual discharge divided by theoretical discharge.
हाँ तो 1.5
means,
लीटर. बाकी का पानी कहाँ गया फिर? बाकी का पानी टैंक खा गई क्या?
सर बाकी का पानी तो टैंक में रहेगा ना फिर?
नहीं तो हमने चालू कर दिया ना टैप, तो अभी नीचे में कितना पानी मिलेगा हमको?
Let me calculate again, sir.
Yes, calculate it. It's a logical questions. Think over it. Yes, from the girl side, Hitesh Barapatre, are you listening to me? Indra Kumar, are you listening to me? Yes, Kajal Kulsunge
Yes.
is there. Kajal. Yes, Indra Kumar is online. Yes, Indra Kumar, please tell me how much quantity of water you will collect at the user end.
Sir, I'm not sure about it. I still calculating.
Okay, you are not sure about it. Madhav, can you tell me? Yes, anybody? Yes, Big Vic, Manisha Pardi. Manisha is there. Nikhil Urkude is there. Nikhil Urkude. Can Nikhil tell me? Yes, Nikhil. Prajwal Tadvekar. Manisha Pardi is online. Manisha?
It's very
Yes,
simple
Shubham.
question.
Hello? सिद्धांत ये 10 सिद्धांत ने आंसर दिया है 105 लीटर पानी, तो 5 लीटर पानी कहां से आया सिद्धांत? एडिशनल पानी कहां से आया? आसमान से गिरा क्या वो टैंक में? पानी तो 100 लीटर ही था ना सिद्धांत, तो 105 लीटर पानी कहां से आया अपने पास?
सर 100 लीटर ही मिलेगा।
हाँ, वेरी गुड कामगार के, वेरी गुड ओके, लॉजिकली योर थॉट, because you see that CD of a venturimeter is nothing but the actual discharge divided by the theoretical discharge. What is the equation of discharge? Meter cube per second. Discharge means rate of flow of water, rate of flow of liquid. Okay, तो वेंचुरीमीटर अगर नहीं है तो आपको शायद कम समय में पानी मिलेगा, लेकिन 100 लीटर मिलेगा। वेंचुरीमीटर अगर है तो rate of flow of water will be lesser. You require more time to collect the water into the bucket or at the user end. But Kamgarde has correctly answered that 100 liters of water पहले था, वेंचुरीमीटर लगाया नहीं लगाया तो भी you will get 100 liters of water. It has nothing to do with the quantity of water. It has to be related with the rate of flow of water. Okay. So very good answer. Okay, let me go to the next part of the my presentation. Okay, so again I will present my screen. So I hope that all of you are listening and all of you are following me during the presentation. So second part of my presentation is basically the dimensional analysis. Okay. So in the dimensional analysis, what are the learning objectives of the dimensional analysis? That is introduction to dimensions and the units, use of dimensional analysis, dimensional homogeneity, methods of dimensional analysis, Rayleigh method, Buckingham method, model analysis. Okay. Model laws of similarity or similarity laws, model and prototype relations. So these are the learning objectives of this section of the presentation. So in many practical real flow problem, the fluid mechanics can be solved by using equations and analytical procedures. However, solutions of some real flow problem depend heavily on experimental data. Sometimes the experimental work in the boundary is not only time consuming but also expensive. So the main goal is to extract maximum information from the fewest experimentation. So in this regard, the dimensional analysis is an important tool that helps in correlating analytical results with experimental data and to predict the prototype behavior from the measurements on the model. Means basically what we study from here is that in case of the dimension analysis, for example, हमें अगर हाइडल पावर स्टेशन तैयार करना है तो हाइडल पावर स्टेशन में हमें हाइड्रोलिक टरबाइन लगेगा, उसका लेआउट डिजाइन करना पड़ेगा, पेस्टॉक डिजाइन करना पड़ेगा, टरबाइन जनरेटर, सिंक्रोनस स्पीड टरबाइन जनरेटर, सारे कंपोनेंट डिजाइन करने पड़ेंगे. सो व्हाट हम लोग एक्चुअल प्रोटोटाइप बना के उसको इंस्टॉल करके उसको टेस्टिंग में नहीं लाते डायरेक्टली. सो व्हाट वी विल डू, okay, that we will do the dimensional analysis. Okay, we will prepare the model replica of the prototype. Okay, we will conduct the experiments on the model, and from the experiments the results will be predicted for the prototype. So In this way, the dimensional analysis is being used in case of the design of the turbine, design of the pump, and design of the many more hydraulic machinery. And it is one of the useful technique in the fluid mechanics or the fluid power, which is used for the design of the various hydraulic power plant. So in dimension analysis, we are only concerned with the nature of the dimension, that is its quality, not its quantity. So dimensions are properties which can be measured. What are the properties that can be measured? Mass, length, time. These are the properties that can be measured. Units are the standard elements which we use to quantify these dimensions. Example, kg, meter, seconds, etc. The following are the fundamental dimensions, and fundamental dimensions last time also we have studied. It is nothing but the MLT, okay, mass, length and time. Then the secondary or the derived dimension. So secondary dimensions are those quantities which possess more than one fundamental dimension, that is area is meter square, volume meter cube, that is L square, L cube, kinematic that is velocity meter per second, acceleration meter per second square, and its dimensions you can see that L by T, L by T square. Then the dynamic, that is force and density, MLT. Newton is nothing but ML divided by T. Okay, so okay, here density kg per meter cube, so M divided by L cube. Okay, so the use of the dimensional analysis. What is the use of the dimension analysis? Conversion from one dimensional unit to another dimension is basically the function of the dimensional analysis, use of the dimension analysis. Checking units of equation, dimensional homogeneity. Okay, defining dimensional relationship using Rayleigh method, using Buckingham Pi method, and the fourth one is nothing but the model analysis. Okay, so these are the applications of dimensional analysis. Then the dimensional homogeneity. Dimensional homogeneity means the dimensions in each equation on both sides equal. So let us consider the equation, that is V is equal to square root of 2gh. Dimensions on left hand side, let us say V is equal to L by T, so LT to the power of -1. Dimensions of right hand side also LT to the power of -1. So dimensions of left hand side is equal to dimensions of right hand side, LT to the power of -1. Therefore equation V is equal to the root of 2gs is dimensionally homogeneous. It can be used in case of system of unit. So dimensional homogeneity can be tested like that. So this equation is V is equal to square root of 2gl. So what we have done is that we have determined the dimensions of the left hand side. So left hand side dimensions are coming out to be LT to the power of -1. Okay, dimensions of right hand side also we have determined LT to the power of -1, which means that this equation V is equal to 2gs, square root of 2gs, is a dimensionally homogeneous equation. Similarly, dimensionally non-homogeneous equation can be tested. So this is the use of the dimensional analysis, which is mostly used in case of the design of the turbine, design of the pump, or the hydroelectric power station. Similarly, another method is there. This method is called as the Rayleigh method. So Rayleigh method is used to define the relationship among the variable. This method is used for determining the expression for a variable which depends upon maximum 3 or 4 variables only. So methodology, let x is a function of x1, x2, x3, and mathematically it can be written as x is equal to function of x1, x2, x3. So this can be written as x is equal to constant k, okay, and x1 to the power of a, x2 to the power of b, x3 to the power of c, where constant k is constant and a, b, c are the arbitrarily chosen power. The value of a, the value of b, and the value of c are obtained by comparing the powers of the fundamental dimensions on both the sides. So this is the Rayleigh method. Let us take one example of the Rayleigh method. Find the expression of discharge in an open channel flow when Q is depends upon the area and velocity. So you know that Q is equal to area into velocity. So K into capital A to the power of small a into V to the power of B. Okay, so where K is a non-dimensional constant, substitute the dimension on both the sides of the equation. So Q is equal to MLT means M to the power of 0. Okay, L to the power of meter cube per second है वो. तो मीटर क्यूब पर सेकंड कैसे एक्सप्रेस करेंगे? L to the power of 3 पर सेकंड मतलब t उसको ऊपर लेके आए न्यूमरेटर साइड में. So t to the power of -1 is equal to K into area. Area is meter square means L square to the power of A, and V velocity, that is meter per second में velocity रहती है. तो L by T, तो L T to the power of -1 is equal to B. So equating the powers of MLT on both the side. So यहाँ पे क्या है? The power of T calculate करेंगे -1. You see here -1 is equal to, okay, minus B. Okay, this is minus B. T to the power of -1 into minus B. So therefore power of B is equal to 1. अब power of L calculate कीजिए. यहाँ पे कितना है? 3. L to the power of 3. So 3 is equal to, okay, here what is the power of L? That is 2A. So here 2A, and here L to the power of B. So it is simply B. Okay, so 2A plus B, that is 2A is equal to 2 minus B is equal to 2 minus 1, क्योंकि B की वैल्यू तो हमने पहले ही फाइंड आउट की है. So 2 minus 1. So power of A is coming out to be 1. So substituting the values of A, B, C in equation 1, that is Q is equal to K into A to the power of 1, V to the power of 1 is equal to VA. So again, okay, we check the this dimensional homogeneity of expression of Q with the help of the Rayleigh method. Similarly, the second equation is given, that is find the equation for the power developed by pump if it depends on H, that is a head, and the discharge Q and specific weight gamma of the fluid. So power of power is expressed as L square mt to the power of -3. Head is expressed as L m to the power of 0 t to the power of 0. Discharge L cube m to the power of 0 t to the power of -1. Similarly, specific weight, and equate this, put it here in the equation. So you can find out the value of C, you can find out the value of B, you can find out the value of A, and substituting this value of A, B, C in the equation. So you will find out that K is equal to 1, and P equation of power जो हमने अभी find out किया है with the help of Rayleigh method is equal to H into Q into gamma. Okay, so this is the equation of power. So this is the equation number 3, that is find the expression of drag force R on a smooth sphere of D moving with a uniform velocity V in a fluid of density rho and a dynamic viscosity mu. Okay, so this is the equation. Function is given, the force Lm t to the power of -2, mass density L cube m and t to the power of 0. Substituting this value and equating the powers of m, powers of t, powers of L, finally we get the equation, that is R is equal to, okay, drag force R is equal to rho v square d square phi in bracket rho v d divided by mu. Okay, so considering all this factor, by equating the powers of the m, t and L, we find this equation for the for expressing the drag force on a smooth sphere of diameter d moving with the velocity v in a fluid of density rho and dynamic viscosity mu. Okay, so similarly the Buckingham pi theorem. So this method of analysis is used when number of variables are more. Rayleigh method 3 to 4 variables are there, then it is easier to apply there, and we use the Rayleigh method. But in case of the Buckingham pi method, okay, the even the complicated problem where the number of variables are more, it can be solved with the help of the Buckingham pi theorem. Okay, so if there are n variables in a physical phenomena and those n variables contain m dimensions, then variables can be arranged into n minus m dimensionless groups called as pi term. Okay, so if the f is the function of x1, x2, x3 up to xn, and variables can be expressed using m dimensions, then f is a function of pi1, pi2, pi3, and pi n minus m, where pi1, pi2, pi3 are dimensionless groups. So each pi term, it contains m plus 1 variables, out of which m are repeating type and one of the non-repeating type. Each pi term being dimensionless, and a dimensional homogeneity can be used to get each pi term. So pi denotes a non-dimensional parameter. So selecting the repeating variable, that is avoid taking the quantity required as the repeating variable. Repeating variables put together should not form dimensionless groups. No two repeating variables should have same dimensions. Repeating variables can be selected from each of the following property. That is geometric property, which is nothing but the length, height, width, and area. Flow property, velocity, acceleration, and discharge. Fluid properties like a mass density, viscosity, and the surface tension. Okay. So taking the example of that is the Buckingham pi theorem method, the pressure difference delta P in a pipe of diameter d and length L due to viscous flow depends on the velocity v, viscosity mu, and density rho. Using Buckingham pi theorem, obtained an expression for delta P. So delta P is a function of d, L, v, mu, rho, or delta P is a function of expressed like that. So total number of variables here, which you can see, is 6. So n is equal to 6. Total number of fundamental dimensions, m is equal to 3. So how many number of terms, pi terms will be there? N minus 3, n minus m. So 6 minus 3, 3 pi terms will be there. Hence the equation is expressed as function of pi1, pi2, pi3. Now each pi1 contains m plus n variable, that is 3 plus 4 variable. Out of 4 variable, 3 are repeating variable. Now choosing the dv mu as a repeating variable, we have pi terms at pi1 is equal to d1 to the power of a, v to the power of b, mu to the power of c1, and delta p. Similarly, pi2 is equal to d to the power of a2, v to the power of b2, mu to the power of c2 into L. Pi3 is d to the power of a3, v to the power of b1, mu to the power of c1, and rho. Okay. So determining the first pi term, second pi term, and the third pi term. So pi1 is equation which you have seen. Substituting the dimensions on both the side, जैसे कि pi1 है नॉन डायमेंशनलेस नंबर है, तो इसलिए क्या आएगा ये ml to the power of mlt 000. So l to diameter का यूनिट क्या रहेगा मीटर. So l to the power of a1 that is lt minus 1. Velocity का equation क्या रहेगा मीटर पर सेकंड. So lt minus 1. Okay. Similarly, viscosity and delta p, and equating the power of mlt, we find out the value of pi1 is nothing but the d delta p divided by mu v. Similarly, we will find out the equation for the second pi term. So second pi term is pi2 is equal to d to the power of a2, v1 to the power of b2, mu to the power of c2 is equal to 1. So equating this one, again we get a second pi term as a L by D. Similarly, we determine the third pi term. Okay. Pi3 is equal to d to the power of a3, v to the power of b3, mu to the power of c3 into rho. So substituting this in the MLT equation, finally we get the pressure difference delta P is a linear function of L by D. Hence L by D taken as the as the function. So delta P is equal to mu V divided by D into L d phi, okay, rho d V mu, which is nothing but the answer for the delta P. So expression for difference of pressure head for a viscous flow. Okay. So likewise, you have to use the Buckingham pi theorem for finding out the pi terms and finding out the expression by equating the powers of the MLT. Okay, model analysis. for predicting the performance of a hydraulic structure such as dams, spillways, hydraulic machine such as turbine and pumps. Before actually constructing or manufacturing model of the structure, or machines are made and tests are conducted on them to obtain the desired information. Okay, in the beginning I told you that before designing the hydro power station or hydraulic turbine, the model is being prepared, okay, which is in dimensional homogeneity with the prototype. The experiments are being conducted, and finally the results or the performance are being predicted, and if any modification is required in the configuration, that can be done in the model itself, so that the prototype should not go into the failure. Okay, so model is a basically the small replica of the actual structure of machine. The actual structure or machine is called as prototype. Models can be smaller or larger than the prototype. So model analysis is actually an experimental method of finding solutions of the complex flow problem. Okay, similitude and similarities. So what do we mean by the similitude? Similitude is defined as the similarity between the model and prototype in every aspect, which means that the model and prototype have a similar properties. So types of similarities: geometric similarity, length, breadth, depth, diameter, area, volume. These are the geometric similarity. Kinematic similarity, velocity and acceleration. Dynamic similarity, time, discharge, force, pressure, intensity, torque, and the power. So geometric similarity, okay, it is being expressed, that is said to be exist between the model and the prototype if the geometry of all corresponding linear dimensions in the model and prototype are basically equal. Kinematic similarity. So what do we mean by the kinematic similarity? That is Vp by Vm is equal to Vr, or Ap by Am is equal to AR, where AR is the acceleration, Vr is the velocity ratio. The kinematic similarity is said to be exist between the model and prototype if the ratios of velocity and acceleration at corresponding points in the model and at the corresponding points in the prototype are same. Dynamic similarity. The dynamic similarity is said to exist between the model and prototype if the ratios of corresponding forces acting on the corresponding points are equal. So Fp by Fm is equal to Fr, where Fr is the force ratio. It means for a dynamic similarity between the model and the prototype, the dimensionless number should be same for a model and the prototype. Okay. Then types of forces acting on a moving body. So inertia force, it is the product of mass and acceleration of the flowing fluid and acts in the direction opposite to the direction of acceleration. It always exists in the fluid flow problem. Similarly, second type of force which is acting, that is the viscous force. It is equal to the product of shear stress due to the viscosity and surface tension of the flow. It is important fluid flow problem where viscosity is having an important role to play. Types of forces acting on a moving fluid. Okay, inertia seen, viscous seen, then the gravity force. What do you mean by the gravity force? It is equal to the product of mass and acceleration due to the gravity of the flowing fluid. It is present in case of the open surface flow. Fourth one, force which is acting is nothing but the pressure force. It is equal to the product of pressure intensity and cross-sectional area of the flowing fluid. It is the represent or it is present in case of the flow of water or flow of liquid in the pipe flow. Surface tension, okay, it is surface tension force Fs. It is equal to the product of surface tension and length of surface of the flowing fluid. Similarly, elastic force acting on a moving fluid. What is the elastic force? It is equal to the product of elastic stress and area of the flowing fluid. Then let us see the dimensionless numbers. Okay, this is very important topic in case of our fluid mechanics. Okay, in case of our fluid power, wherein we are studying this dimensionless number and it is being used. So dimensionless numbers are obtained by dividing the inertia force by viscous force or gravity force or pressure force or surface tension force or the elastic force. So Reynolds number, what is Reynolds number? Reynolds number is nothing but the rho v d by mu. So Reynolds number is basically inertia force by the viscous force. Rho v d by mu. V is nothing but the velocity of fluid in the pipe. D is nothing but the diameter. Mu is viscosity. Okay, rho is density. So what with the Reynolds number, what we do is that we categorize the type of the flow, type of the liquid flow. For example, if the Reynolds number is lesser than 2000, then the flow is laminar flow. If the Reynolds number is greater than 2000, we say that the flow is turbulent flow. Okay, so you might have experimented and used this concept of Reynolds number in case of your laboratory experiments in the fluid power. Okay, in the subject of fluid mechanics or fluid power. So Reynolds number is used to predict the type of flow in case of the liquid, that is laminar flow, transitional flow, or the turbulent flow, and it is given as inertia force by viscous force. Similarly, the Froude's number, it is given as square root of inertia force divided by gravity force. Euler's number is given by inertia force by pressure force. Weber's number is given by inertia force by surface tension force, and the Mach number is used by given by the elastic force by inertia force by elastic force is equal to V by C. So Reynolds number is used for predict the type of flow in case of the liquid gas. In case of the gases, the Mach number is used to predict the type of flow. We say that supersonic supersonic speed, sonic speed, subsonic speed. So depending upon the Mach number, if the Mach number is greater than 1, supersonic speed. Okay, if Mach number is equal to 1, sonic speed. If the Mach number is less than 1, it is nothing but the subsonic speed. So what is the Mach number? Mach number is nothing but the inertia force divided by elastic force, that is the V by C. So these are the dimensionless numbers which is used in the fluid mechanics, okay, to obtain all these things. So before I go to the next part of my presentation, let me take the review that what I have covered, which topic I have covered in the second part of my presentation. So can anybody answer that what are the topics covered by me in the second part of the presentation? Yes, anyone? Akash Bavankar, Akshay Srirame. Akash Bavankar, Akshay Srirame. Can anybody tell me that what are the topics I have covered in the second part of my presentation? Dolly Vasnik, are you here?
Dimensional analysis, in which
Sir, dimensional
Just a
unit.
minute. First chance I will give to the Shubham, then I will come to the Tamgadge. Shubham.
sir, dimensional analysis in which we studied Buckingham Pie method and Rayleigh method.
Okay, very good. Very good. Tamgadge? Bahuddan Tamgadge?
Yes, in dimensional analysis, fundamental dimensions and derived dimensions we have studied.
Okay.
And Rayleigh method and Buckingham method.
Okay.
Plus dimensionless numbers. Dimensionless numbers we have studied.
Okay. Very good, Tamgadge. So can anybody answer that what is the purpose of dimensional analysis, or what are the applications of dimensional analysis? Shri Surusai, Sagar Rai, can anybody answer? Saurabh Vaidya?
To define property and element, sir.
Sanket, Sanket, bolo Sanket.
To define property and element.
To define property and elements, but clarify it, means to define property and elements means what basically? Can you clarify on this?
Conversion from one dimension to another dimension.
Conversion of one dimension to the no basically
Another dimension.
नहीं वो भी नहीं है हाँ बहुत दिन
Checking unit.
हाँ बोलो तामगाड़ी
Checking units.
हाँ हाँ बोलो
Conversion from one dimension to another. Checking
no
units.
it is not only the conversion, the basic use is that जैसे कि हाइडल पावर स्टेशन हमें अगर डिजाइन करना हाँ
Dimensional analysis is used at design of various power plants.
हाँ डिजाइन मीन्स व्हाट हैपेंस हम लोग जो है अपने टरबाइन की आमिर कुछ बोलना चाहते हो आमिर
नहीं सर आप बोलिए सर.
हाँ सो हम लोग अगर डिजाइन करना चाहते हैं हाइडल पावर स्टेशन ओके तो आपको पता है कि टरबाइन की साइज ओके कितनी बड़ी रहती है और कितने साइज का रहता है तो इसलिए कैसा है कि हम लोग अगर डायरेक्टली प्रोटोटाइप बनाएंगे एक्चुअल टरबाइन बनाएंगे और अगर वो एक्चुअल टरबाइन प्रॉपर फंक्शन नहीं करता है प्रॉपर अगर काम नहीं करता है सो इन दैट केस ओके व्हाट विल हैपन our complete money goes into the waste. So instead of that what we do we prepare a model एक छोटा मॉडल बनाते हैं वो मॉडल इट इज इन डायमेंशनल होमोजेनिटी विद द प्रोटोटाइप प्रोटोटाइप डिजाइन करने के बाद में प्रोटोटाइप का एक मॉडल बनाते हैं छोटा और वो मॉडल के ऊपर हम एक्सपेरिमेंटेशन करते हैं एंड बाय कंडक्टिंग द एक्सपेरिमेंटेशन द मॉडल हम टरबाइन के रनर एंगल है गाइड वेन्स है गाइड वेन का एंगल है पेन स्टॉक का डिजाइन है सर्च टैंक का डिजाइन है सारी चीजें हम पहले ही मॉडल के ऊपर एक्सपेरिमेंट कंडक्ट करके डिजाइन कर लेते हैं सो दैट अगर हमारा जो है परफॉर्मेंस नहीं दे रहा है टरबाइन की इफिशिएंसी नहीं मिल रही है मॉडल में तो हम उसको पैरामीटर को इम्प्रूव करें ओके सो वी डेवलप द मॉडल्स विच आर बेसिकली इन डायमेंशनल होमोजेनिटी विद द एक्चुअल प्रोटोटाइप we conduct the experiments on the model itself and if the model is not performing we can discard also so cost of discarding will be very less क्योंकि प्रोटोटाइप बनाएंगे और फिर पता चलेगा कि ये तो काम ही नहीं कर रहा है तो इन दैट केस द कंप्लीट एनर्जी मैन पावर मनी इट इज बीइंग वेस्टेड so because of that while designing the hydel power station while designing the pumps and the machinery we prepare the मॉडल विच इज इन डायमेंशनल होमोजेनिटी विद द एक्चुअल प्रोटोटाइप और हम उसके ऊपर एक्सपेरिमेंट करके जो है वो बाद में इसका एप्लीकेशन वहां पे आता है डायमेंशन एनालिसिस का सो दैट वी कैन प्रिडिक्ट द रिजल्ट एंड वी कैन गो फॉर द प्रोटोटाइप मैन्युफैक्चरिंग ओके सो मान लीजिए कि अभी हमको मतलब किसी भी केस में हम यूज कर सकते हैं प्रोटोटाइप डेवलप करने के पहले मॉडल के ऊपर टेस्ट करके कर सकते हैं सो क्या हाँ आमिर क्या बोल रहे थे आप आमिर ओके सो हैव यू गॉट माय पॉइंट ओके सो लेट मी आस्क यू द अनदर क्वेश्चन व्हाट इज द function of the Reynolds number what is the function of Reynolds number how to express the Reynolds
The function of Reynolds number sir the function of Reynolds number is we categorize the various types of flow
yes very good Amit
mirror flow laminar flow turbulent flow
yes laminar flow transitional flow turbulent flow very good so how it is expressed Reynolds number कैसा एक्सप्रेस करते हैं इनर्शिया फोर्स बाय विस्कस फोर्स ठीक है Reynolds number is expressed as inertia force by viscous force so what is the purpose of the Mach number Mach number का क्या यूज है Mach number can anybody tell me what is the purpose of the Mach number yes Sanket Dhokli is online
yes. Elastic flow inner flow upon elastic flow
it predicts the type of
flow sir
Sanket?
Inertia flow upon elastic flow.
Okay. Inertia force by elastic flow. Okay, inertia force by elastic force. Very good. But उसका use क्या है? मैक नंबर से क्या करते हैं?
It can define speed, sir.
Yes, which we can define the flow of gases. Okay, तो क्या होती है स्पीड या ये फ्लो, टाइप ऑफ फ्लो इन गैसेस क्या क्या होता है?
Greater than 1, sir, or less than 1.
ग्रेटर देन
hypersonic.
उसको संकेत क्या बोलते हैं?
Hypersonic.
Yes, supersonic flow, sonic flow, and the subsonic flow. If the Mach number is greater than 1, it is a supersonic flow. If the Mach number is equal to 1, it is a sonic flow. If the Mach number is lesser than 1, it is a subsonic flow. So this part of the presentation, it is over, and now I am moving on to the third part of my presentation. Let us see the some of the gate examples. So is it visible to you? My screen is visible. Can anybody tell?
Yes, sir.
Yes, sir.
Okay, thank you. So the previous gate examination we will cover up now. A phenomena is modeled using n-dimensional variables with k primary dimensions. The number of non-dimensional variables. This was the question in the gate 2010. Gate 2012. Okay. So, and you have to choose the correct option. So phenomena is modeled using an n-dimensional variable with k primary dimensions. So here the a is equal to k, b is equal to n, c is equal to n minus k, or n plus k. Okay, so dimensional मैंने बताया था आपको कि n minus m होता है, तो यहाँ पे with k primary dimensions दिए हैं. Okay, k primary dimensions दिए हैं. So n minus k. Answer, correct answer is n minus k. Match the following. Again, this is the question from the GATE 2010 examination. Okay, that is a compressible flow. Okay, free surface flow, boundary layer flow, pipe flow, heat convection. So try to match it. Here, Reynolds number, Nusselt number, Weber number, Froude number, Mach number, and the 5 options are given. Okay, sorry, 6 options are given. Skin friction drag. So try to match it. Okay, which is the correct answer. So what we can see that, let us say compressible flow. So compressible flow, air is nothing but the compressible. Okay, gases are compressible. So naturally in compressible flow, Mach number will come into picture. Okay, that is subsonic flow, sonic flow, supersonic flow. Then the free surface flow. Okay, free surface flow, we have studied that the Weber number will come into picture. So Weber number. Okay, then in case of the boundary layer flow, okay, boundary layer flow, the skin friction drag will come into the picture. Similarly, pipe flow. So pipe flow is nothing but the, just now we have studied, that is Reynolds number will come into picture. And heat convection. So in heat convection, the Nusselt number will be there. Okay, so Nusselt number is nothing but the V. So correct option is D, correct option, that is P, Y, Q, W, R, Z, S, U, and T, V. Similarly, Grashof number signifies the ratio of inertia force to viscous force, okay, or the buoyancy force to viscous force, or buoyancy force to inertia force. So which one is correct now? Okay, Grashof number is connected with the buoyancy force to the viscous force. So this is the GATE 2016 examination question. So answer B is correct. The relationship between the length scale ratio LR and the velocity scale ratio VR in hydraulic model in which fluid dynamic similarity is maintained. So this is the question of the GATE 2015. Okay, answer correct is VR is equal to root of LR. Now same, that is GATE 2013. Group 1 contains the dimensionless parameter and group 2 contains the ratios. You can see that this is group 1, that is a Mach number, Reynolds number, Weber number, Fruits number, or group 2, ratio of inertia force, gravity force, viscous force, like that. You have to choose the which is the correct option. इसका अभी आप बताइए कौन सा आंसर है करके, because just now we have studied. Try to answer. Can anybody answer? Anyone from the girl side? Which answer is correct? Hello? Mach number, Reynolds number, Weber number, Fruit number. You have to, in the group 2, you have to arrange it. Which answer is correct? Okay, let us see. Answer C is correct. So Mach number is nothing but the ratio of fluid viscosity to the velocity of sound. Okay, then the Reynolds number is nothing but the ratio of inertial force to viscous force. Weber number is equal to the ratio of fluid velocity, R2, ratio of fluid velocity to the velocity of sound. And Fruit number, that is ratio of inertial force to the surface tension force. And the Fruit number is nothing but the ratio of inertial force to the gravitational force. So likewise you have to answer. Then which of the following statements are true for dimensional analysis? The functional relationship between the dependent and non-dependent variable can be expressed into dimensionless term by dimensional analysis. So in model testing, it reduces the number of variables into 3 number. It is used to change the theoretical equation into dimensionless form. It helps to convert the units of dimensions from one system to the another. So which statement is true here? Okay, because 1 2 3 or 1 3 4 or 1 3 2 3 4 or 1 3 4 or 1 2 3 4 all are correct. Okay, so the dimensional analysis में क्या होता है कि functional relationship between the dependent and non-dependent variable can be expressed into dimensionless term by dimensional analysis. 2 भी true है क्योंकि in model testing it reduces the number of variable into 3 number. 3 is also correct. It is used to change the theoretical equation into dimensionless form. 4th is also correct. It helps to convert the units of quantities from one system to the another system. So option D is basically correct. The next question is in front of you. The unit of physical quantity which does not depend on the unit of any other physical quantity is called as independent dimension, fundamental dimension, core dimension, none of the above. बहुत easy question है ये. So it is called as the, which is the physical quantity which is not dependent on the unit quantity or any other physical quantity is basically called as the fundamental dimension. Okay. Then the next one, you try to see the question number 8. What are the dimensions of the force? What are the dimensions of the force? So dimensions of the force are nothing but the option A is correct. That is M, L and T to the power of -2. Whereas equations of the dimensions of force are given. So you must know the equation of force. Accordingly, you can calculate. Okay, match the following physical quantities in group 1 with their dimensions in the group 2. So work energy, power, momentum, modulus of elasticity and dynamic viscosity. इसको टर्म के साथ में मैच करना है. ओके, सो वर्क डन के लिए क्या है, ml square to the power of t to the power of minus 1 के लिए c है. Okay, so for 1 it is c, that is this one. For 2 it is ml square. Okay, means power के लिए ml square and t to the power of minus 3. So d, that is d4 is there, means modulus of elasticity. Okay, ml t to the power of minus 1 and 5b. Okay, so likewise you have to select your answer. Which of the following is a dimensionless equation? रेनॉल्ड नंबर, ऑयलर्स इक्वेशन, वेबर्स इक्वेशन. कौन सा नंबर इसमें से डायमेंशनलेस नंबर्स है? ठीक है, डायमेंशनलेस इक्वेशन है. सो ऑल आर डायमेंशनलेस इक्वेशन. So with this I conclude with the first part of my presentation. Okay, and let me continue with the let me take the review and then we will continue with the second part of the presentation. So let me know which topic we have covered today. Can anybody, अभी हमने क्या लिया third part of the presentation में, which topic we have covered? Manish Bhoyer, Pradeep Harinkhede.
So in third topic we take previous gate questions.
Okay, Shubham, very good. Can anybody tell that what was the nature of the any gate question that you can say, which you have asked, which you have seen? कौन से टॉपिक के ऊपर था? Manisha, can you tell? Manisha is online. Manisha Pardi, are you listening to me?
Sir, dimension analysis.
Yes. Okay, very good. So be on the line, Manisha. Always try to listen what I am teaching you. Okay. So this is the second part of the presentation. We will have the 2 minutes break and immediately we will start. Okay, the third part of the next part of the presentation. Okay. So don't get log out. Within 2 minutes we will start. Let me present my screen. हे चालू आहे ना बेटा, चालू आहे रे, चालू आहे, व्हिडिओ चालू आहे. Okay, are you able to see my screen? Can anybody answer?
Yes, sir. Clearly visible.
So we will go through the next topic in the fluid power, that is flow through pipes. Okay. So contents of this presentation, that is characteristics of flow through pipes. Okay, and the second one is the energy losses in flow through pipes. Major losses such as loss of head due to friction, Darcy-Weisbach formula. Minor losses such as loss of head at entry, change in diameter bend. Okay, problems on head losses, hydraulic gradient line, total energy line, effect of entry at pipe, change in diameter bend and hydraulic gradient line and total energy line, plotting hydraulic gradient line and TEL, and design of pipeline for given flow using formulae, using nomograms, and the computation of height of reservoir, compound pipe and equivalent sizes. So this is the um, contents of my next part, this part of the presentation. Let us see how much we can cover. Because of the time limitation, we have to end up somewhere in between. So laminar flow, when the fluid flow moves slowly in layers in a pipe without much mixing among the layer. Okay, that is nothing but the laminar flow. So you know that the ink pen is there. So in the ink pen, what happens that when you are writing, the flow of ink from the pen, from the nib, is nothing but the laminar flow. Okay, what is the turbulent flow is a different one. So it typically offers when the velocity is low or the fluid is very viscous. Okay, in case of the laminar flow. What is turbulent flow? Opposite of the laminar flow, where considerable mixing occurs and the velocities are high. Laminar and turbulent flow can be characterized at and quantified using the Reynolds number. So we know that Reynolds number is basically the rho v d by mu, okay, which is used to characterize the flow type of flow, that is laminar flow or turbulent flow. Okay, and here you can see that the mixing of particles are there. Particles are not moving in a streamlined pattern like a laminar flow. So considering the example in the of the laminar flow and turbulent flow, what you can see is that you see the flow of water once you open the tap in the wash basin and put the cup over there. Okay, so what happens, this portion of the flow of water which is being issued from the tap is nothing but these particles are moving in a laminar nature, laminar manner, and here the splashing of water which is being taking place. So there is a mixing of the particles of the water. So this particular flow is characterized as a turbulent flow, and this flow is nothing but the laminar flow. And how to identify it, how to determine it, it is given by the Reynolds number rho Vd by mu. So the definitions, that is layers of water flow over one another at different speeds and virtually no mixing between the layers. The flow velocity profile for laminar flow in a circular pipe is parabolic in shape, with maximum flow in the center of the pipe and a minimum flow at the pipe wall. The average flow velocity is approximately 1/2 of the maximum velocity. Turbulent flow is characterized by the irregular movement of the particles of the fluid. The flow velocity profile for turbulent flow is fairly flat across the central section of the flow and drops rapidly extremely close to the wall. The average flow velocity is approximately equal to the velocity at the center of the pipe. So viscosity is the fluid property that measures the resistance of a fluid to deforming due to the shear force. For most of the fluid, temperature and viscosity are inversely proportional. So this is the definition of the laminar flow. turbulent flow, and the viscosity. Now we will go to the types of the losses. Okay, so what are the various types of losses? So types of losses majorly this is being categorized into two: minor losses and major losses. And minor losses are nothing but sudden enlargement, okay, sudden contraction, sudden entrance at the exit due to pipe fitting. मतलब कैसे है कि एक पाइपलाइन में देयर आर मेनी फिटिंग्स आर देयर, ओके, बेंड होता है, एनलार्जमेंट होता है, कॉन्ट्रैक्शन होता है, एंट्रेंस में लॉस होता है, एग्जिट में लॉस होता है. So these are all the minor losses, okay, and the major loss is nothing but the loss of head due to friction. Okay, so loss of head due to friction is termed as the major loss. It depends on the velocity of the flow, okay, and diameter of pipe and roughness. It is denoted by HF. So HF is nothing but the FLV square by 2GD. What is F? F is coefficient of friction, L is length of the pipe, V is velocity of the flow. So V square divided by 2G, G is acceleration due to gravity, and D is diameter of the pipe. So HF is equal to FLV square by 2GD, which is basically the major loss in case of the flow of liquid through the pipe. And the minor losses, which you can see, the diagram you can see, that is, it is due to the distribution of the flow pattern. That is loss of due to sudden enlargement or sudden contraction. What you can see that here area is less, here area is more. So sudden expansion of the flow of water which is being taking place, due to which there is a energy loss. Okay, loss of head due to sudden contraction. This example you can see that sudden contraction, it is due to the sudden contraction of the pipe, denoted by HC. So HC is equal to, in bracket, 1 by CC minus 1 square divided by XV square divided by 2G. Okay, loss of head or loss at the exit, it is head loss at the exit of the pipe, it is denoted by HEX. So a pipeline say water is allowed to enter into the container, so the exit losses will be there. HEX is equal to V square by 2G. Similarly, loss due to pipe fittings, that is it is due to the pipe fitting like elbows, walls, etc. It is denoted by HB. So HB is equal to K into V square by 2G. यहाँ पे बेंड है, ओके, पाइप फिटिंग में यहाँ पे एल्बो है, वॉल्स है. So there are the minor losses which are taking place because of the pipe fitting. Then loss at the entrance, you can see here the diagram, loss at the entrance, which is given by HEN is equal to 0.5 V square by 2G. Okay, so it is loss at the entrance of the pipe. Then the frictional losses in the pipe, so it varies with the laminar or turbulent flow. So energy equation can be given as, okay, you know that P1 by rho G plus V1 square by 2G plus Z1 is equal to HA minus HR plus HL, okay, is equal to P2 by rho G plus V2 square by 2G plus Z2. What is HA? HA, HR and HL are the heads associated with the addition, removal and friction loss in pipes respectively. Okay, the head loss in pipes, HL, can be expressed as by the Darcy's equation for energy loss. So in general form, the Darcy equation is expressed as 4F1L1 V square divided by 2GD, where F is a friction factor, L is the length of pipe, D is the diameter of pipe, and V is the velocity of the pipe. Okay, so I think with this we will stop here, and in our next class we will start with the minor losses, major losses, and all these things, and its hydraulic gradient line. Okay, flow through nozzle, water hammer effects in pipe. We will take some example, solved example, and the previous gate examination. So with this, I end up my lecture here, and let us go to the your queries. I will try to solve your queries, and then we will end with this lecture. So any queries, any other thing?
Anyone is having any question? Anyone want to ask any question?
Any question, any queries? Tamgarge? Any question, any query? Can anybody? Bolo.
If anyone having any queries, kindly please ask to sir regarding our today's topic on fluid mechanics.
Okay, can anybody let me know in this part of the presentation which topic I have covered now? Ritesh Bhoyer, Suroshe, are you here? Saurabh Vaidya, are you here? Shrikant Gharde, are you listening to me? Indra Kumar Dhawale is online. Yes. Indra Kumar, can you tell me that which topic I have covered now in this part of the presentation? Last part of the presentation?
Flow through pipes. We have studied types of flow and losses, minor and major losses during the flow through pipes.
Okay, very good, very good. Okay, very good. Saurabh, you were saying something. Saurabh Vaidya, आप कुछ बोल रहे थे? हाँ, yes.
सर वो फ्लो एक और क्या बोला सर उसमें माइनर लॉसेस मेजर लॉसेस.
हाँ, major losses and minor losses. Huh? Okay. Next question to you is that minor losses. Okay, can you categorize minor losses? क्यों होते हैं minor losses? किस चीज से होते हैं? Why it happens? Minor losses in a pipe.
Sudden contraction, enlargement.
Yeah, sudden contraction, enlargement. Wall is there, bend is there. Okay, due to the pipe fittings, there will be a minor losses. Now, can anybody answer that what are the major losses which is being occurring in a pipeline? Amar Dhok, can you answer? Amrit Roy, are you listening to me? Arpit Ramte.
So major losses due to friction.
Okay, major losses due to the friction, loss of it due to friction. Okay, very good, Shubham. Huh? Very good. So, if any query is there, let me answer the query. Otherwise, Vishwajit, we will end the today's lecture. Already 12:20 is over. Is there?
If anyone having,
Sir, I have one query regarding.
Yes, Tamgad, bolo.
ऑरिफिस मीटर में जो होल रहता है उसमें हम एंगल देते हैं, तो ऑरिफिस मीटर का जो प्लेट रहता है, बीच में जो रहता है वो रहता है, तो उसका एंगल उसमें देते हैं, तो उसको थिकनेस कैसे कैलकुलेट करते हैं? वो प्लेट का
थिकनेस कैसे कैलकुलेट करेंगे? हमारे पास इनलेट डायमीटर है. इनलेट डायमीटर मतलब फ्रंट साइड में जी फ्लो के डायरेक्शन में जो डायमीटर है वो डायमीटर हमारे पास अवेलेबल है. ठीक है. और दूसरे साइड में डाउनस्ट्रीम साइड में मतलब फ्लो के दूसरे साइड में जो डायमीटर है वो डायमीटर अवेलेबल है. ओके, इट इज अ स्मॉल होल विच इज देयर इन द ऑरिफिस प्लेट. So with the help of the diameter, we calculate the angle which is being given, because there should not be any abrupt change. Okay, वो जो वहाँ पे जो पास होता है, so there will be a frictional losses also which will be taking place when it passes onto the surface of the orifice plate. So the angle through or the curve which is being given, that can be calculated with the help of the diameter. And what diameter we are expecting? Diameter of the flow of water at a point of vena contracta. मतलब वेना कॉन्ट्रैक्टा पॉइंट मतलब कहाँ पे है? डायमीटर ऑफ इनिशियली जो फ्लो ऑफ वाटर का पाइप का फ्लो जो है वो पाइप का डायमीटर है. बाद में बाहर निकलने के बाद में वो कॉन्ट्रैक्ट हो जाता है और उसका डायमीटर जेट फॉर्म होता है, उसका डायमीटर कम है. So where the diameter is less, that point is nothing but the vena contracta. So with the help of this, okay, we calculate the angle to be provided onto the surface of a orifice plate. Okay, so that there should not be any major losses should be minimum as possible. At the same time, we should be able to measure the flow rate of the water or the liquid. Okay, so very good question. Very good. Both. Any other question?
Sir, I think that now students didn't have any queries regarding today's topic.
Okay. So shall we end now?
Yes, sir. Yes, sir.
Okay. Thank you.
Once again, good morning, good afternoon to all. As now we come to the end of today's wonderful lecture on fluid mechanics, it was indeed privilege to have a Dr. G.K. Awari, sir, HOD Automobile Engineering Department, Government Polytechnic, Nagpur. His today's insightful lecture on fluid mechanics was full of wisdom and information in that he shared wonderful tips to use the optimal use of our mind to solve a critical problem on the of the gate so that our student can easily solve the gate numericals. I feel that students who attended today's class get a maximum knowledge for upcoming gate examination. Once again, at the end of our today's lecture, I thank you, sir, for having spared your valuable and precious time for all of us. Thank you, sir.
Thank you.
Thank you so much, sir.
Yes, sir.